All right, here's another think pair share. And this think pair share is maybe presenting something that, you know, um, is maybe a little bit off from what you would expect, um, but no less difficult, okay, than the previous examples here. So let's just get into it, and I think you'll see right away what I'm talking about. Absenteeism of college students from math classes is a major concern to math instructors because missing class appears to increase the drop rate. Suppose that a study was done to determine if the actual student absenteeism rate follows faculty perception. So here on the left, the faculty expected that a group of 100 students would miss class according to the following table. So you can see here, it appears as though we've got four categories, right? Which means that K is going to be equal to 4. And between 0 and 2 absences, the faculty expect 50 students would be absent. Between 3 and 5, 30 students. Between 6 and 8, 12 students. And 9 or more absences per turn, they would expect 8 students to miss 9 or more absences. Now, this column on the right says a random survey across all mathematics courses was then done to determine the actual number of absences in a course. The table below shows the results of the survey. So with these different categories, we have the number of student absences being 35, 40, 20, and 5. So, right now you might be thinking, okay, well, are the probabilities uniform, for each category? Sorry, my laptop is thinking. Okay, give me a moment. Apologize for the delay. Okay, not sure what's going on. Okay, there we go. All right, so you're probably asking, well, okay, so are the probabilities of each category uniform, or are the probabilities non-uniform? Because if it's uniform, then you would calculate the expected value this way, and if they're non-uniform, you would calculate the expected value that way. But this is an example of where you don't even need to calculate the expected value because, right, a random survey, okay, conducting a survey, those are observed values. And then what the faculty expected, well, there's your expected value. So you already had everything you needed. You didn't have to worry about that formula or that one. These are the observed, these are the expected. Okay, so this didn't really have so much to do with probabilities of things like we would think of with, dice, for example, but just the human expectation of math faculty. Okay. So we're going to conduct a hypothesis test to see if what the faculty expect, is backed up by evidence, by observation. All right. So, in a way, we're just going to kind of cut to the chase a little bit. So I think at this point, we could think about, like what's the null hypothesis? So the null hypothesis is that our observed student absenteeism, I'm going to say matches faculty perception. Or not faculty perception, let's go ahead and say faculty expectation. As soon as I get to bring up my eraser. Okay. Faculty expectation. And that's going to be our original claim. And then the null hypothesis is that the observed student absenteeism does not match faculty expectation. All right. So we have 4 categories, which means that our degrees of freedom, which is k minus 1, is going to be equal to 3. And what was our sample size? Well, actually, I don't think we need it, but our sample size would just be adding up all these values. So let's see, what, 35 and 5, that would give us 40. 40 plus 40 is 80. Then 80 plus 20 is 100. Yeah, so I don't think we need that. Okay, let's just kind of have it there. Let's see. We weren't given any information about the confidence level or the significance level. So I'm just going to put no confidence level given. Therefore, a 95% confidence level can be assumed. And that means we've got a significance level of 0.05. All right. Yeah, we've got room here. So let's see, this is kind of like a mashup of step 1 and step 2 together. And so step 3 would be to calculate our chi-squared test statistic as well as our p-value. All right. So we need to use our goodness of fit test. So I went ahead and I put in the observed and the expected. Okay, over here, same, observe and expected. And then we'll go to tests. I'm going to scroll up because I know goodness of fit is closer to the bottom. And since I put observed first, that was in list 1, expected is list 2. But now we've got 3 degrees of freedom. So I'll go ahead and hit calculate. Okay, so we got chi-squared of 14.29 and a p-value of 0.0025. Now let's just confirm. Okay, so that 2 is list 1 and list 2. Yeah, 14.29 and 0.0025 looks good so far. Num works. Okay, we want to go to the inference app. Go to tests. We want a chi-squared test, goodness of fit. And I put in the observed and the expected values. It put in degrees of freedom for me because it's 1 less than the number of rows that we've got. We do have a significance level of 5%, so that's right. And we get 14.29 and 0.0025. Okay, so we get chi-squared test of 14.29 and a p-value, a probability value of 0.0025. All right, let's go to the next page and I will write this down. There we go. Let's Scroll down some more. Good. So step 4 is going to be to sketch the distribution. So it's chi-squared, so it's not symmetric. It looks right skewed. So something about like that. So it'll always be right-tailed. So here's our chi-squared critical value, which we still need. Okay, your significance level is 0.05. That's the area adjacent to the critical value. Reject the null is above the tail. Fail to reject is above the confidence level. All right, so in order to get this critical value, we have to use an inverse distribution function. So I'll just do it on one of these Texas Instruments calculators. Maybe just to be fair, I'll do it with this one. Okay. There we go. All right, so we have a significance level of 0.05 with 3 degrees of freedom. So we get a critical value of 7.81. Okay, numworks. Let's go to the distribution app. Chi-squared, 3 degrees of freedom. Area to the right, an area of 0.05. 7.81. All right. So we have a critical value of 7.81. And so our test statistic is 14.29. So 14.29 is clearly going to be up here. Which if we draw up, telling us to reject the null. And, our p-value is 0.0025. That's the area here in this tail, which is really super tiny. So comparing, oranges to oranges and apples to apples, okay, apples to apples, it's reject the null. Comparing area to area, if p is smaller, reject the nuller. And so here p is definitely smaller than our significance level. So that's telling us to reject the null as well. Okay, trying to switch to black. There we go. So now I'll go ahead and scroll down and let's give our results and write our conclusion. So step 5 is to write down our results and our conclusion. So we just said that we're going to reject the null, and the null was our original claim. So null is the original claim. We're rejecting the null. So we're going to say there is sufficient evidence to support rejection of the claim. All right, so let's go ahead and write that down. There is sufficient evidence to support rejection of the claim that observed student absenteeism matches faculty perception okay, with a 95% confidence level. All right, that's our conclusion. Okay, let me know if you have any questions.